Hey, all you cool physics cats and kittens. Let's take a look at impulse and momentum. We're going to take a look at chapter 9, but just focus on section 1 for right now, because I don't want to get, too ahead of ourselves. Let's take a look at something you've probably heard of before, momentum. You can probably think about momentum when you imagine skiing or sleigh riding, and you know that the more mass you have on that sled or on those skis, the faster you can go. And also, the longer amount of time that you're moving, the faster you go. And so, momentum can be very fun. But in physics, we are going to look more at the formula side of things. And momentum requires three things. First, you have to have a moving body. It has to have mass, and you have to have time. If we take a look at the momentum formula, you'll see we have P, which stands for momentum, M for mass, and V for velocity. And then the units are simply kilogram meters per second. Impulse, on the other hand, might be something that you think about, like when you're at home. Girls, you may understand this. Sometimes I load up my Amazon cart on impulse. You know, it's like that sort of impulse is something you might be familiar with. In physics, though, impulse is related to momentum, but it may not be something that, you've really heard of before. So I'm going to try to take this kind of slow. And impulse is simply the change of momentum. So if you're going down the hill on a sled and you hit a tree, that moment of impact is referred to as impulse because it changes your momentum. Or even if you just hit a dry patch when you're skiing, that changes your momentum. And that moment of change is again called impulse. Impulse is a vector quantity. If you remember that vectors, they have both magnitude and direction. Magnitude is just a fancy physics word for number. So it has a number and it has a direction. The direction of impulse is always in the direction of the net force. So let's take a look at the formula for impulse. I accidentally included the whole impulse momentum theory, but I want you to take a look at it with me. So first of all, we have over here, we've got a change in momentum. And that is actually the definition of what impulse is. It is the change in momentum. But how do you find that change? You have an average force or a net force and a change in time. And that is equal to impulse. Now, in your book, I really don't know why, but it doesn't use I for impulse. It only uses this, this portion of the formula to stand for impulse. So if I accidentally switch to I on any of my lectures or in any of my formulas, please just remember your book only has this, but it means the same thing. The average force times the change the average force times the change in time. So this ninth chapter in the first section talks about impulse momentum theorem. We already know that impulse is the change in momentum of an object when the object is acted upon by an outside force for any amount of time. So the theorem that we use is right here. This is the impulse part of the theorem, and this is the momentum part of the theorem. And we're going to use these both together and separately to find impulse or momentum, and then we use them together to find different aspects of larger problems. I know you can't wait. The things I want you to remember as you're working through these problems are just your basics. Anytime you see that little change, that little triangle, the delta that stands for change, that simply means the final minus the initial. So in momentum, we see the final momentum minus the initial momentum. Or in time, the final time minus the initial time. Or velocity, final velocity minus the initial velocity. These are basics that I don't want you to forget about. All right, so we're going to try a couple practice problems together. So I'd like for you to look at page 238 in your physics books. And let me go over this with you. So we're going to look at average force. A 2,200 kilogram vehicle traveling at 94 kilometers per hour, that is 26 meters per second, can be stopped in 21 seconds by gently applying the brakes. It can be stopped in 3.8 seconds if the driver slams on the brakes, or it can be stopped in 0.22 seconds if the vehicle hits a concrete wall. What is the impulse exerted on the vehicle, and what is the average force exerted on the vehicle in each of these stops? Okay, we kick it off with a giant problem. So let's break it down. First of all, what do we know? Well, we know the mass, we know the initial velocity, and we know that we want to come to a complete stop, so we know that the final velocity in all of our problem is going to be 0. And we have 3 different changes of time. We have the gentle braking, we have the slamming on the brakes, and we have, oops, I hit a wall. So what are we actually trying to find out? Well, we're trying to find out the impulse of gentle braking, hard braking, or crashing into a wall. And in order to do that, we actually need to back up for a few seconds. So I don't know if you can read this. You know how my eyes are. But I went ahead and worked this out for you. So the first thing we need to do for the problem is to solve for momentum. And that's because the change in momentum equals impulse. So let's take a look at our initial momentum. Our initial momentum is our mass, the 2,200 kilograms, times our velocity, our initial velocity, which is 26 meters per second. And so that's going to give us 57,200 kilogram meters per second. But let's break that down in 5.72 times 10 to the 4th kilogram meters per second. So that's what I'm going to use. And it's in a positive direction. Now, the final momentum is 0 because it doesn't matter your mass if your velocity is 0. Correct? Correct. All right. Now we're going to take that number right here, and we are going to use, oh shoot, hold on. It just disappeared for me. And now we're going to use the impulse momentum theorem to solve it. So, you see this is our impulse momentum theorem right here. Well, it's part of it. So, we're going to use force times the change in time equals our change in momentum. The final momentum minus initial momentum. So that's going to be 0, because that's where we're stopped, minus the 5.72 times 10 to the 4th kilogram meters per second. Well, now I need to get force by itself, because that's the only thing I don't know. So I'm going to divide both sides by change in time. That's going to cross out. So now I have negative, because of it changed to negative up here. Negative 5.72 times 10 to the 4th kilogram meters per second divided by our change in time. Well, for that first gentle braking, our time is 21 seconds. So if you do your math and divide this out, you are going to get negative 2.7 times 10 to the 3rd newtons. Now you might be thinking, wait a minute, how in the world did we get newtons out of all of this? Well, remember that a newton is mass times acceleration. So we have kilograms, which is our mass, times meters per second, which is acceleration. So that is how we got, to newtons, okay? Now we are going to use the exact same change in momentum to solve for the other forces. So I used the same change in momentum, which was the negative 5.7, actually it was 5.72, sorry, times 10 to the 4th. And I set it up with force times the change in time. I divide by the change in time, cancels that out. And now I'm going to do the hard braking. And the time for the hard braking was 3.8 seconds. So I'm going to multiply this again, right? Or I'm sorry, I'm going to divide this again. And I'm going to come up with negative 1.5 times 10 to the 4th newtons. And then finally, my same momentum divided by the change in time for hitting a concrete wall. So I want you to do those calculations. And if you divide the negative 5.7 times 10 to the 4th divided by 0.22 seconds, again, you'll get negative 2.6, this time times 10 to the 5th newtons. Because I want you to think about it. Obviously, it's going to require more force to hit a concrete wall than it is to simply slam on the brakes. Now, I know that just by doing one practice problem, you're not feeling very confident yet. So let's try another. I want you to take a look at number 1 on page 239. And forgive my spelling errors. It's hard for me to see my stupid computer. All right. A compact car with a mass of 725 kilograms is moving at 115 kilometers per hour toward the east. Sketch the moving car. Well, we'll get to that. But the first thing I think of is, kilometers per hour? I really want to convert that to meters per second, because that's the only way we're going to get to newtons. So I used differential analysis to convert. And you just start here with 115 kilometers per hour. Now I'm going to solve for my kilometers first. You see here, 1 kilometer, so that cancels out, is equal to 1,000 meters. Good, we've already got our meters. So now let's deal with our time. So we have per hour. Well, we want rid of that. So here, I've got 1 hour is the same as 60 minutes. So now that cancels out my hours, but I don't want meters per minute. So we have 1 minute is the same as 60 seconds, Well, now that cancels out my minutes, and I am left with meters per second. And if you do your math, that rounds out to right about 32 meters per second. So when you do your velocity, we are going to use this as our velocity, okay? So I told you I'd sketch my car. Please forgive my sketch. So here's my car. It looks like a little sombrero with wheels. But my car is going 32 meters per second east. Now, the problem asks us to find A, the magnitude and the direction of the momentum. So first of all, you should refer back to what the momentum equation is. Well, lucky for you, I brought it forward for us. So here's the momentum equation. And we are trying to find the magnitude and direction of the momentum of this compact car. So it's simply mass times velocity. So we plug in the mass, the 725 kilograms, and we just multiply by the 32 meters per second. And you will see that that calculates to 2.32 times 10 to the fourth kilogram meters per second east. Of course, we're not done. We have a part B. So, part B states, a second car with a mass of 2,175 kilograms has the same momentum. What is its velocity? Ooh, that's a little trickier. So we're going to solve that one together. So again, we are using the formula for momentum, but we know that we are solving for velocity. So we want to get velocity by itself, right? So if you come down here, I took the original formula, the momentum times mass times velocity, and I divided both sides by its mass, so that cancels out. And now I have momentum divided by mass is equal to velocity. Now I want you to just plug in your numbers. Remember, we have the same momentum we had the last time divided by a different mass. What velocity do you get? Well, you will probably get right around 10.6 meters per second, or if you wanted to go ahead and work it all the way back out, trust me, you don't have to, it would work out to 38.4 kilometers per hour. I hope that helps. Now, your assignment. So, before I talk to you again on Tuesday, I'd really like you to complete numbers 2, 3, and 4 on page 239. And I know parents may not understand why I only assign you maybe 2 or 3 problems at a time, but I know you guys understand. So, I'd like for you to work those out the best you can. If you get stuck, just remember, I'm going to work them out with you on Tuesday. I just want you not to be overwhelmed, okay? Well, you guys have a great day, and I'll talk to you later. Bye, guys.